Hello. Today we're going to be looking at a parametric equations problem. So this problem here, it says find the area of the region enclosed by the asteroid denoted by this set of parametric equations. So in order to find the area of this figure here, it's important to recall the area has to be equal to the integral of y dx. And if y is a function of t and so is x, it's important to remember that if we write this as a differential, dx equal to f prime of t dt like this, we can rewrite this integral as g of t f prime of t dt. This is the equation that we can use to calculate the area of this asteroid. Now, this formula is dependent on the y value being greater than or equal to 0. Otherwise, we get a negative number. Now, using this formula, let's take this upper portion of this asteroid. This is a symmetrical figure here. So why don't we use this formula here and try to calculate this upper portion of the asteroid here. And this is just half of the total area that we're looking for. And we'll get it in terms of A. A is the height of this asteroid as well as the width. So once we find this upper region, we'll just multiply by 2 and we'll get the full region. So we're going to take this formula. We're given a set of parametric equations. Instead of a function of t, it's going to be a function of theta, but that doesn't really make that big of a difference. So let's just rewrite this set of parametric equations. Y is equal to a sine to the third of theta. X is equal to a cosine to the third power of theta. Now, let's use our formula here. Before I do that, I'll erase some of this. Great. So now let's take our A has to be equal to, and we'll talk about I'll talk about the limits of integration. So when theta is equal to 0, it starts at this point on the asteroid. It starts on the very right hand side. And when theta is equal to pi, it goes all the way to this side. So the path is sort of from here to here, from 0 to pi. And it goes through the whole circle. So as it traverses through 2 pi, it traverses through this entire figure, much like a circle. But instead of a circle, the parametric equations of a circle, it would just be a cosine theta and a sine theta. But because of this third power, it like moves the circle part inwards. So circle, it looks something like this. But because of the third power here, it kind of shifts it in the circle inwards like this. So a brief note on that. So our limits of integration are really just going to be 0 to pi, and the actual area is going to be twice this, because this is only the equation for the top part of the asteroid. So let's take this, let's put in our value for y, a sine cubed theta, and let's find dx. We have to write it as a differential. Dx is just going to be equal to the derivative of this, which is negative 3a cosine squared theta sine theta, and multiplied by the differential of d theta. Negative 3a cosine squared theta sine theta d theta. So let us simplify this a little bit. So this gets us negative 6a squared 0 to pi of sine to the 4 theta and times cosine squared theta d theta. And we can solve this integral. This is, it does have a closed form, this integral here. So let me make a little bit of space. So notice that this integral here is the same thing as sine squared theta times sine theta cosine theta squared d theta. And notice a couple of things. I'll point out some trig identities. Notice that cosine of 2 theta is equal to 1 minus 2 sine squared theta. So I can rewrite this as sine squared theta is equal to 1 minus cosine 2 theta over 2. And also recall that sine of 2 theta is equal to 2 sine theta cosine theta. So that means that sine theta cosine theta is equal to sine 2 theta by 2. Fair enough. So we can rewrite this entire expression in terms of these two sort of quantities. So I will give myself more space like that. And let's take a look. So we can rewrite this entire expression as minus 6a squared 0 to pi sine squared theta. We said this was equal to 1 minus cosine 2 theta over 2. And we said sine theta cosine theta was sine 2 theta over 2. And this is squared. So this now, we can simplify this more. 6a squared 0 to pi times 1 minus 1 over 2. I'll distribute the 2 here. Cosine 2 theta over 2 times sine squared 2 theta over 2 d theta. So I'm going to distribute this entire expression. This is just a bunch of simplification. 0 to pi. Then I'll do, this becomes sine squared. Sorry, I apologize. This should be a 4 because 2 squared is 4. 2 squared 2 theta over 8 minus sine squared 2 theta times cosine of 2 theta divided by 8 once again. And the differential, it's still d theta right there. So we can split this single integral into two separate integrals, and we can solve them independently and come up with an answer. So minus 6a squared, we can divide this into the integral minus 6a squared over 8 sine squared 2 theta d theta minus, or I should say plus 6a squared over 8 0 to pi sine squared 2 theta cosine 2 theta d theta. So let us continue and let's solve these two integrals independently so we can get the form of the solution for both of these integrals. So first, let's just find the indefinite integrals. Sine of 2 theta, I'm sorry, I believe it was sine squared 2 theta, if I'm not mistaken. Yes, it was sine squared 2 theta d theta right here. We'll just find the form of the indefinite integral first. So we already talked about, if you recall from the identity, cosine 2 theta is equal to 1 minus 2 sine squared theta. Well, we can, and we from this we found that sine squared theta is equal to 1 minus cosine 2 theta over 2. Well, we can apply this to sine squared 2 theta is equal to 1 minus cosine 4 theta over 2. And we can replace this expression with this 1 minus cosine 4 theta over 2 d theta. And we once again get two more smaller integrals to work with here. 1/2 minus cosine 4 theta over 2 d theta. But fortunately, these are much easier integrals. So this is just d theta of 2 minus cosine 4 theta over 2 d theta. These are just much simpler integrals to work with. So this becomes theta over 2 minus sine 4 theta over 8 plus c. So that's one of these integrals solved. So that's great. Now I'll make some more space once again. There we go. And the second sort of integral that we're working with here is this one here. Sine squared 2 theta times cosine 2 theta. And this is also a simple integral. This is just a u substitution. So I'll find the form of the indefinite integral first. So sine squared 2 theta cosine 2 theta. This is just a u substitution. I just set u equal to sine of 2 theta like this. Du is equal to 2 cosine 2 theta d theta. So, which is, I can rewrite this du over 2 is equal to cosine 2 theta d theta. Once again, I need more space. So I can just set this equal to 1/2 u squared du, which is equal to u cubed over 2 plus c, which is equal to, because u is equal to sine 2 theta, this is equal to sine cubed 2 theta over 2 plus c. So we found the two forms, we found these two indefinite integrals here, theta over 2 minus sine 4 theta over 8 plus c, and sine cubed 2 theta over 2 plus c. So let's put them back into this original, but we'll now use the limits of integration instead of this plus c. So for this one, I'll just factor out negative 6a squared over 8 for now. So this distribution was a little pointless, but that's okay. So I'll just find, I'll just copy theta over 2 minus, what was it again? Minus sine 4 theta over 8, sine 4 theta over 8, and sine cubed 2 theta over 2. That was the other one. sine cubed 2 theta, I believe. Yeah, sine cubed 2 theta over 2. My mistake. And we'll set this from 0 to pi. Now, notice that when we do this, when we take these limits, that these terms will cancel because the sine of 4 pi is equal to 0, and the sine of 0 is equal to 0, and the sine of 2 pi is equal to 0, and the sine of 0 is equal to 0. So these terms are just 0 minus 0. They just go away. So it's really just this term that I have to worry about here when I'm doing the calculation. And this becomes negative 6a squared over 8 times pi over 2 minus 0, which is just negative 6a squared pi over 16, which simplifies to negative 3. I should have simplified this a long time ago, but here it is, like that. So this should be our area. But wait a minute now. It's a negative number here. A is a positive number. A is just the length or width of the asteroid. So why is this a negative number here? The reason is because if you recall from a while back, I'll zoom out. We've done a lot of work here, but if we go back to the original, when we took this differential, notice that this differential is negative. The reason it's negative is because when we're going along this path here, we're really going backwards like this. We're going in a counterclockwise manner backwards. And when we do this, our x is actually decreasing. So our derivative of x with respect to theta is actually negative. So an integral is basically just, we're taking areas of many, many, many small rectangles like this, but this dx value is negative. So these areas are also going to be negative. And that's why we're getting a negative number here, because this would be the same thing as taking the integral going backwards, like a backwards integral. You might recall, if you might recall actually that the integral, kind of a rule of integrals. If I make some space here, kind of a rule of integrals is that a to b is equal to the negative of b to a, because I'm taking Riemann sums with a negative value for each base of the rectangle. That's why this value is the opposite of this value, and that's why we get a negative number, because the base of each rectangle that we're using in our Riemann sums is actually negative because our x is decreasing. But not to worry, it just means that the area is the magnitude of this expression, which is equal to 3a squared pi over 8. And that is the final answer. And this is the area of the asteroid in terms of A. All right. I hope that was helpful. Thank you for watching.